Shrinkage compensators, delta R, and shear wall performance. This equation is used by structural engineers to calculate wall drift deflection. It is made up of 4 parts. The first part is bending. The second part is shear. The third part of this equation is on fastener slip. And the fourth is delta A, or deflection due to anchorage. This deflection includes elongation of rod, crushing of wood from the bearing plate, and deflection of the shrinkage compensator. This is in 2 parts. Deflection due to load, and 2, delta R, the average travel and seating increment according to ICC AC 316. This graph shows a dramatic difference delta R can make in a deflection of a tie-down system. Showing all the components of delta sub A in equation 23-2, this is comparing a ratchet type device, or TUD, and a screw type TUD. Note that the rod and the bearing plate deflection is the same. The deflection due to the load is very similar, but the delta R in red is very different. In fact, it's over 100 thousandths difference, almost doubling the deflection of the anchorage. In 2001, the city of Los Angeles ran a series of tests on shear walls. Its purpose was investigating the effects of free movement on hold-down anchorages. The free movement was allowed was 200 thousandths of an inch. In the result of this test, the nominal shear load was reduced to about 60% of the mean. In other words, only shear wall anchorage systems can perform as designed if they're tight. As little as 200 thousandths movement, and it reduced the performance by 40%. That's 40%. To demonstrate delta R in practical terms, we will use a shrinking wall model. The lower floor of the model will shrink to simulate wood shrinkage and building settling. The rods are fixed. The middle dial indicator measures the change in the floor height. The side indicator measures the delta R movement in respect to the shear wall due to the shrinkage compensators. The left wall has ratchet type compensators, or TUDs, and the right wall has screw type compensators, or TUDs. First, we'll begin by activating the screw TUDs by removing the set screws. This releases the internal springs and allows it to expand as the floor system shrinks and settles. This keeps the shear walls tight. Next, while the wall systems are still freshly installed, we test the lateral looseness by moving the walls back and forth. This is the delta R. Now we shrink the wall. Note the middle dial indicator showing the movement of the floor. The screw type TUDs begin to expand, keeping exact pace with the floor movement, maintaining a tight shear wall. Lateral movement against the wall show very little delta R deflection. After resetting the ratchet side, you'll see the same movement of the dial as earlier. This is because delta R is an inherent portion of the design, and it cannot be removed. Shrinking the floor gives us the same results. Very little deflection on the screw type TUD. The ratchet side shows the same amount, 50 times as much as the screw type TUD. It doesn't matter how much you shrink the floor, you will still have the same reaction. Very little movement on the screw type side and a great deal of movement on the ratchet side. It's an inherent part of the design. It cannot be removed. The ratchets have to do this in order to, in this case, go down the rod and make up for that shrinkage. Only a tight system can perform as designed. Because delta R is inherent, it cannot be removed, and it will create a looser shear wall. The delta R can double the anchorage deflection with a ratchet type device. Keep the shear walls tight using auto tight, the screw type TUDs.